Hello, this is Kuntal Chakraborty, Assistant Professor of Electrical Engineering Department, Greater Kolkata College of Engineering and Management, JIS Group. I'm just going to give a lecture on an important topic, that is a single-phase induction type energy meter. First, we will try to explain the constructions of single-phase induction type energy meter. In case of single-phase induction type energy meter, we have four different main parts, that is the driving system, moving system, braking system and recording mechanism. In case of driving systems, basically we have two magnets that is basically used for the driving, and the moving systems we have some a disc is connected with these moving systems, and we have ball bearings and shaft will be there. And in case of braking systems, we have a braking magnet that will use for the braking systems. And the recording mechanism we have by which we can record the energy consumed by the system. So individually I am just going to discuss all the system elaborately from the next slides. First is a driving system. It basically consists of two magnets. One is a series magnet and another one is a shunt magnet. Series magnet, it basically consists of number of U-shaped laminations of silicon steel together to form a core, that is U-shaped, and a coil of thick wire having a few turns is wounded on this U-shaped magnet. Both the legs of the U-shaped, means like this way. This is a U-shaped magnet we have, that is a series magnet, and the wires that is actually wounded on these two legs of this U. And the coil is known as a current coil, which is connected series with the load. So means if load is connected with this system, so at that time the current that will be flow through this magnet, coil, and at that time that will be magnetized due to flow of current. So it produces a magnetic field proportional and in phase with the line current I. Similarly, we have the shunt magnet. It consists of a number of M-shaped laminations of silicon steel assembled together to form a core, and a coil of thin wire having a large number of turns is wounded on a central limb of this magnet. So now if you see the M-shaped magnet in the central limb of this magnet, so the coils are wounded on this, thin coils are wounded on this, and that is thick, and the number of coils is larger than the current coil. So this coil is connected across the load, and thus it is excited by the current proportional to the supply voltage, that we actually provide a supply voltage to this magnet, so that basically the electromagnet basically work with the proportional current of the supplied voltage to it. So that is the driving system by which the we can drive the overall system. Next is a moving system. The moving system eccentrically consists of a light rotating aluminum disc mounted on the vertical spindle or shaft. The shaft that supports the aluminum disc is connected by the gear arrangement to the clock mechanism on the front of the meter to provide information that consumed energy by the load. So the rotation of this aluminum disc that is connected in between the shaft or the gear systems, that will provide the informations that is consumed by the load. So here the disc is connected with a spindle, and that is connected with a gear system, and this gear system is connected with a recording mechanism systems by which the recording that can be done, what amount of energy actually consumed by the systems that can be recorded. So the time varying fluxes, that is the sinusoidal fluxes produced by the shunt and series magnet, induced eddy currents in this aluminum disc, and the interaction between these two magnetic fields and the eddy currents set up a driving torque to this disc so that the moving system can move. Means that due to that the disc that will move. So basically what is happening, these two magnetic field that will produce the eddy current into the disc. So this magnetic field as well as the eddy current that will interact, and due to that the disc that will move. So that's why there will be the system that will move. The interaction between these two magnetic fields and the eddy current sets up a driving torque in this system. So the number of rotations of the disc, therefore, the proportional to the energy consumed by the load in the certain time interval, and is commonly measured in kilowatt hour method. So that is the moving system. Next is a braking system. Damping of the disc is provided by a small permanent magnet that is located diametrically opposite to the AC magnets. So here this is a braking magnet that is connected diametrically with this system, magnetic systems. So that will provide that when the disc is moving through this permanent magnet, at that time the field, the magnetic flux that will be cutted by the disc, and at that time the eddy current induced in this disc. Now the movement of this rotating disc through the magnetic field crossing the air gap sets up eddy current in the disc, and that reacts with the magnetic fields and exerts a braking torque. So that is the system by which the braking that can be done, and by changing the position of the braking magnet or diverting some of the flux, the speed of the rotating disc that can be controlled. So that is the constructions of the braking system. Next is the recording system. As I discussed, when the moving system moved with this system, the gear arrangement is connected with this system, so that the recording that can be done. The functions of recording or registering the mechanism is to record continuously a number of the on the dial which is proportional to the revolution made by the disc. So the number of revolution on the disc is measured, the electrical energy passing through the meter. So that is the overall constructions of the energy meter. Next is the operating principle. The basic principle of the induction type energy meter is electromagnetic inductions. When the alternating current flow through the two suitably located coils, as we know that the current that will flow through the series magnet as it is connected with the load, at the same time we will provide a voltage to the shunt magnet, so that equivalent current of the voltage that will be flowed through this magnet, and these two magnets that will produce the rotating magnetic field, and which is cut by the metallic disc suspended near the coil. Thus the EMF induced on this disc which circulates the eddy current. So that is the interaction made between this rotating magnetic field and the eddy current. So that's why the torque that will develop on this disc. So when the energy meter is connected in the circuit, the current coil carries the load current that I already discussed, and the pressure coil carries the current proportional to the supply voltage, that is I also already discussed. The magnetic field produced by this series magnet in phase with the line current, and magnetic field produced by the shunt magnet is in quadrature with the applied voltage. So thus a phase difference exists between these fluxes produced by the two coils. So there will be some phase differences between these fluxes that is produced by the coils, and this will actually set up the rotating magnetic field which interacts with the disc and produce a driving torque on this disc. So the disc will start rotating. The number of revolutions made by the disc depend on the energy passing through this meter, means the spindle gear to the recording mechanism, so that the energy consumed in this circuit is directly registered in kilowatt hour method. So that is the operating principle. Basically will provide the current to the series magnet, as it is connected with the load, as well as we will provide the voltage to the shunt magnet, so its equivalent current that will flow through it, and these two magnet actually produces the EMF, and due to this two magnetic field, the disc will rotate and it will induce a eddy current. So the interaction made between this magnetic field and the eddy currents, so that's why the disc that will rotate. So that is the operating principles of energy meter. So here we have the cross side view, where we are seeing that a disc is connected with the ball bearing systems, and here we have the M-shaped shunt magnet. In the central limb, the thicker coils are connected, and here in this section we have the series magnets, where the coils are wounded on this series magnet, and these coils are not it's a small amount of coils are connected here. So here we have the permanent magnet that will provide the braking system, that will basically provide the braking of the system, and this is the side view of the energy meter. Next, I'm just going to discuss the driving torque. Here we have already discussed the two fluxes and two eddy currents, therefore two torques are produced by the first flux phi c, that is generated by the current coil, interacting with the eddy current IP generated by the flux P, that is produced by the pressure coil or the shunt coil, and second flux phi P interacting with the eddy current IC generated by the phi C, means the series coil or the series magnet generated by phi C, and that will interact with the that is actually generate the IC, and that will interact with the flux of the generated by the pressure coil or shunt coil, and this interaction made and two torques that will produce. So basically the flux produced by the shunt magnet phi P lags behind the applied voltage V almost 90 degree. So basically here we have the phi P, and here the voltage applied is V, so near about to 90 degree lags the phi P by V, and the phi C is produced by the load current I. Phi C is produced by the load current I, and phi C is in the direction of I. So here the phi C is in the direction of I. We are seeing in the phasor diagram. So now here the flux phi P and phi C induced in this disc, which will produce the eddy current in this disc, that I already discussed, and the reaction between these fluxes and eddy currents produces the driving torque. Let phi P and phi C are the two fluxes having the phase difference beta. Here we are seeing that phi P and phi C has a phase difference, that is beta, and here phi P is equal, say phi P is equal phi m1 sine omega t, and phi C, that is equal phi m2 sine omega t minus beta. So as you know that the phase difference is beta, so that will be omega t minus beta. So the RMS value of the flux is phi P, that will be equal to phi m1 by root 2, and phi C, that will equal to phi m2 by root 2. So we know EP, that is which is proportional with the minus d phi P by dt. So now that is proportional, as we know the phi P is equal that is phi P is equal phi m1 sine omega t. Now we can replace this equation into here. So d of phi m1 sine omega t by dt. So now if we differentiate it, then we will get minus omega phi m1 cos omega t. Now if you try to simplify it, then omega will be to pi f. So now that will be proportional with the minus f phi m1 cos omega t EP, here the EP lags the flux by 90 degree. Here the EP is lagged by the phi P by 90 degree. So now the RMS value of EMF is EP. So EP, which is proportional with the F phi M 1 by root 2. So that can be written as proportional F phi P. So AD current is IP, that is the RMS value. IP, that will be equal to EP by Z. Here we are getting EP, which is proportional F phi P. So now we can replace it. So that will be proportional F phi P by Z, where Z is the impedance of the eddy current path. So now the average torque produced by the interaction of the phi C and IP, the interaction between the phi C, the flux produced by the current coil, and the eddy current due to the pressure coil or the shunt coil. So that will produce a first torque, that is T1, which is proportional phi C IP cos 90 degree plus alpha plus beta. So the angle between phi C and IP, here the phi C and IP we have, this angle is 90 degree in between phi P and EP. This one is alpha and this one is beta. So that will be 90 degree plus alpha plus beta. So that's why 90 degree plus beta plus alpha. And similarly the TD2, which is proportional with the phi P IC cos 90 degree minus beta plus alpha, that is produced, there is a flux of the shunt magnet and the interaction between the shunt of the flux magnet and the eddy current produced by the current coil. So now the angle between the phi P and IC is 90 degree minus beta plus alpha. So here the phi P, here we have the phi P and this one is IC. So the angle between IC and EC is alpha here, and the angle between EC and phi C is 90 degree minus beta. 90 degree phi P and EC, that is 90 degree minus beta. So that's why that is 90 degree minus beta plus alpha. So TD2, that is proportional phi P IC F by Z cos 90 degree minus beta plus alpha. So now the total torque is the difference between the two forces, that is TD is equal to TD2 minus TD1. So now we can replace the TD2 and TD1 here. So that will be proportional phi P phi C F by Z cos 90 degree minus alpha plus beta minus phi P phi C cos 90 degree plus alpha plus beta. So now if you try to simplify it, then that will be proportional to phi P phi C F by Z sin beta minus alpha plus sin beta plus alpha. Now again, if you try to simplify it, then that will be proportional with phi P phi C F by Z sin beta cos alpha. So but here the phi P, which is proportional with the voltage that is provided by the that is provided into the shunt magnet, and phi C, which is proportional with the I, that is the load current. So now we can write it as the beta here is del minus phi, here the beta is del minus phi. So now the TD that can be written is equal K1 phi P phi C F by Z sin del minus phi into cos alpha. So now here the F, Z as well as alpha, these are the constants. So that's why we can write the equation as TD, that is equal to K2 V into I sin del minus phi. If n is the steady speed, the braking torque, that will be proportional with the steady speed. So that's why TB, which is proportional with the n. Now we can write TB, that is equal to K3n. So at steady speed, as we know that the braking torque and driving torque will be the same, as I already discussed. So K3n, that will be equal to K2 Vi sin del minus phi. Here is del is near about to 90 degree. Here is a del is near about equal to 90 degrees. So now if we del is equal 90 degree, then n, that will be equal to K2 by K3 Vi sin 90 degree minus phi. So now K2 by K3 that can be written as K, and sine 90 degree minus phi, that will be equal to cos phi. So now N, that is equal to K VI cos phi. So the speed, that will be equal to K VI cos phi. So K into power. Now the total number of revolutions, that is if you integrate in terms of time, so integration N dt, so K VI cos phi dt, that will be equal to K integration power dt, that is K into energy. So that is the way by which we can calculate the energy in a single phase induction type energy meter. Now is the breaking torque, which is very important, as we actually discussed. And here in this arrangement, we actually provide a permanent magnet, and the disc moves through this permanent magnet, and it will cut some flux that is generated by the permanent magnet, and due to that the eddy current induced, and that will actually give the braking torque, and that will provide the braking torque. So now the braking torque is produced by the eddy current that I already discussed, induced in the disc by the rotation of the magnetic field of a constant intensity. So the constant field basically provided by the permanent magnet. So the eddy current IB produced in the aluminum disc by the brake magnet, that is the flux, that is the phi B, and which is proportional with the speed N. So now the braking torque, that is TB, which is proportional to the phi B IB. So here IB, that can be written as EB by R, and R is the eddy current path of the resistance, and that EB, which is proportional with the N phi B. So now we can write proportional phi B N phi B by R, so that is proportional with the N phi B square. So here the phi B is constant, so now the TB, that is basically proportional with the speed. So as we know, at steady speed TB is equal TD. So now VI cos phi, that is proportional with the N. So speed of the disc is proportional to the power consumed by the load, and the total number of revolution, that is I already discussed, that is integration d N dt, that is VI cos phi dt, that is proportional energy consumed. And this means that the speed of the rotation of the disc is proportional to the average power, and the integral of the number of revolutions of the disc is proportional to the total energy supplied. So that is the system by which the braking that can be done by in case of single phase induction type energy meter. So I already discussed in this section the constructions of the single phase energy meter, as well as braking torque, driving torque, as well as the operating principles of the single phase induction type energy meter. So to prepare this lecture, I took the help of these books. So these books helps me a lot to prepare this lecture, as well as the NPTEL lectures by the IITs, that is actually helped me a lot to prepare this lecture. Thank you.